Hello? Axel. Right, we'll get started again. So this is our last talk on MEP today, and then we'll follow up with a discussion. And then there's actually a number of posters at 5 that you can view that are relevant also to this MEP issue. So very pleased to have Jonathan Gregory here with us from Reading. He's going to talk about diagnosing entropy production in GCMs, I guess. Cheers. All yours.
Thank you for asking me to speak too. And also, Peter introduced me to MEP by lending me Paltridge's paper when we shared an office in Bracknell a long time ago. I would like to describe work. It's really interesting having heard the previous 2 talks today and how there are interesting relationships between this work and what's already been presented. So this work that I want to present is actually the work of my PhD student Salvatore Pasquale, who is here. Salvatore is at the moment busy writing his thesis and writing papers about this, and that's why he's not giving this talk. But I'm sure he'll be very happy to join the discussion. And Martin Ambaum and Rémi Tailleur, who are also not here, are Salvatore's co-supervisors in Reading, and we've had an interesting time talking about these things together. So the motivation, as you are by now aware, is the possible use of a couple of conjectures as constraints on climate modelling. One of them is the constraint of Ed Lorenz, suggested in 1960, about atmospheric general circulation operating at near its maximum possible rate, by which he meant maximum possible generation and therefore dissipation of kinetic energy. And then there is the suggestion of Paltridge in 1975 and various subsequent papers that the Earth atmosphere system, which is the most active part of the climate system, is attempting to maximize entropy production. But he also mentioned, and of course he cited Lorenz's paper, maximum dissipation. He saw these things as quite closely related, and of course they are related under certain assumptions, which we'll come to later on. Well, step back. Of course, these ideas are exciting to physicists and to climate modelers because they offer the possibility of setting integral constraints on climate models without, and this is the point, having to know in advance all the details. Perhaps they would offer a way to constrain or formulate models if you know what the answer is that you're aiming at, which is kind of what Tim said. Since we know what the realistic climate system is, perhaps these principles would tell us what the model was, so to speak, and that's why we thought it would be interesting to look at. But most work that's been done, as Tim also showed, on the application of these principles has been done with climate models which are simplified in more or less severe ways, although Puma is which is the most advanced one that Tim talked about, is a general circulation model. It still doesn't have the complexity of the kinds of models that are practically used to make climate projection during the 21st century, and in a sense that's why we're interested in climate modelling to a large extent. So the aim of this project was to attempt to see whether we could apply these principles to a climate model of that kind, and that is an atmosphere-ocean general circulation model. And HADCM3 was a possible candidate for doing this. It wouldn't be quite right to describe HADCM3 as a state-of-the-art model because it's now quite an elderly model, having been developed in the late 1990s. But it's still, in terms of its simulation, it compares well with some much more recently developed models, and it's computationally relatively cheap, but not cheap enough for all of these purposes. And so we actually did most of the work with FAMOUS, which is a low-resolution version of HADCM3, but has the advantage of having essentially the same physical formulation except for its resolution. So it's a 3-dimensional atmosphere model coupled to a 3-dimensional ocean model with representations of clouds, radiation, advection, and so on. And FAMOUS, as you see, has about half the spatial resolution and runs more than 10 times faster, so that makes it suitable for experiments which either are running over long time scales or, in this case, where you want to do a large ensemble of experiments. And the lower picture shows the error in of the simulation of the climatological surface air temperature, the difference with respect to the crew climatology. On the left is HADCM3, on the right of FAMOUS. And you can see that the errors, so white is within 1 degree of the observed climatology. The errors in FAMUS are more severe than those in HADCM3. You can't have something for nothing, and it's a cheaper model. It will not produce such a realistic solution. But the patterns are really quite similar. In absolute terms, its simulation is really very good. It also simulates climate change, the patterns of global temperature change during CO2 forced climate change very similarly to HADCM3. So while clearly it's got limitations, we judged a model that was sufficiently representative of this class of climate models to be useful for this purpose. Now let me remind you about how MEP has been argued to come about in simple models like the 2-box model. These are using diagrams of axles, in fact. And he has called this a trade-off mechanism. So the climate system is driven by the flow of heat down the temperature gradient from low latitudes to high latitudes, as depicted in this picture of axles here. And so entropy is generated because this meridional heat flux is going from a high tropical temperature to a cooler polar temperature. And the trade-off is that if we increase this meridional heat flux, we will reduce the temperature difference between the pole and the equator. So this picture shows how the temperature difference declines as we increase the heat flux. And because the entropy production is proportional to the difference in temperature divided by the square of the mean temperature, that means that somewhere between the extremes of no heat flux and no temperature difference, there'll be a maximum entropy. And this is why it's called a trade-off. So it could be that this same mechanism would operate in a GCM. That's what we'd like to investigate, whether we get a maximization by that kind of means. But of course, there's a lot more going on in a GCM than just a meridional heat flux, like in a 2-box model. Another picture of Axels, in fact, illustrates this. So there are various kinds of entropy production going on in the system. First of all, we've got the entropy that's added to the system when the solar flux is absorbed, either at the surface or in the atmosphere. And then we have a loss of entropy by the climate system when net long-wave radiation occurs. So that the atmosphere and the surface are both losing heat by long-wave radiation, gaining heat by short-wave radiation. So that's one part of entropy production associated with radiation. Then there is another part that Goody distinguished from this by calling it irreversible, which has to do with considering the difference between the temperature at which the sun emitted the radiation and the temperature at which the Earth absorbs it in the case of the solar flux. There's a very big difference. So now we're talking about taking this large heat flux through a large temperature difference, so that corresponds to a large amount of entropy production. And then there is a corresponding term on the long wave side. As far as the climate system is concerned, what we're interested in is the net rate of loss of long wave. But in fact, most of the climate system cannot radiate long wave radiation directly to space. A lot of emission and reabsorption goes on inside the atmosphere, and that is also a source of entropy production. But you might consider, and indeed has generally been considered, that these irreversible radiation contributions are not really relevant. You can imagine the climate system would do exactly the same thing if we replaced the radiation input and output by local heaters or cooling mechanisms. We could drive exactly the same circulation in the same way. So whether it's the sun of our colour that's heating it up, for instance, can't really be relevant to the climate system. So we probably don't have to consider that part. And then finally, there's the part contained in this red box here, which we call material entropy production, which is how the system itself transfers the heat from the places where it's absorbed, where the solar radiation is absorbed, to the places where the net long-wave radiation occurs. And that is what is driving the climate system. So that is sensible heat transfer from the surface into the atmosphere and within the atmosphere, latent heat likewise, and frictional heating of the atmosphere when the kinetic energy is dissipated. So that's the heating within the atmosphere. So this is what we're mostly interested in, the material entropy production. So we can write down some simple equations for these budgets. So thinking about these three things separately. As far as the climate system is concerned, it takes in radiation and it loses radiation, short wave and long wave, and it transfers heat within itself. That's the material entropy production. And overall, this adds up to 0 because the amount in the steady state, it must add up to 0. The Did I mean to write that? Yeah, no, okay, no, yeah, right. Locally, there is also locally a heat balance. So locally, the material heat flux must be balanced by the radiative heat convergence within the climate system. So we locally have zero and globally a zero integral. At the top of the atmosphere, we have, from the radiation's point of view, we have these two terms, both the irreversible production of entropy that has to do with the difference in the temperature of the incoming and outgoing radiation, and the part where the radiation disappears into the climate system as shortwave and then reappears as longwave radiation. And then if we add these two equations together, we get that the top of atmosphere planetary radiation flux is the sum of the entropy generated, entropy flux is the sum of the entropy generated within the climate system and the entropy generated by the irreversible transformation of radiation temperatures, which we're not going to consider to be relevant to the climate system. So that's the planetary entropy budget. So we can diagnose all these things from a GCM, and our first task is therefore to do that. So as regards the material entropy reduction, we've got the dissipation of Ke within the system, and then we have things that transport heat down the temperature gradient within the system. And I'm omitting here other entropy terms that come from, potentially that come from a diffusion of mass or chemical reactions or whatever, which are not represented in the model. However, GCMs aren't really formulated in these kinds of terms. This is how we calculate it in a box model. We consider a heat flux between this temperature and that temperature. But a GCM is not formulated in terms of processes that take heat from one temperature to another temperature. It's formulated instead in rather like sources and sinks. There are things in some places that take heat out of the atmosphere, and then there are other for example, like evaporation. And then there are other things like condensation that release it somewhere else. And these are not done by the same schemes necessarily in the model, and there's no clear connection between them. So we instead have to reformulate it. So instead of the dot product for a flux and a temperature gradient, we instead reformulate it in terms of a heat convergence, and then there's a boundary heat flux. So if we take an integral over the whole system, provided there is no material heat flux into the system, then of course these two things are equal. So we can work out the entropy production instead by considering the local convergence and divergence of heat. And that should give us the same answer. But still that imposes a restriction, because it means we do have to, although this is sort of looks like a boundary term, we also have to exclude internal sources and sinks of heat. So we still, in particular with the hydrological cycle, we have to consider in the end the hydrological cycle as one process, because it takes latent heat from some places and it puts it in other places. And unless we consider all these things added up, we won't get a zero heat sum. So before we get to that stage, nonetheless, we install extra code in the model to diagnose each of the processes that is responsible for a local entropy source or sink. And of course that's easy to do. It's just the local heat flux. So it relates to the local rate of change of temperature, and in a finite difference formulation that means we just have to consider how much the temperature has changed over a time step and divide it by the temperature. And so we can output three-dimensional diagnostics of these quantities. So before we get to the heat transport terms, let's talk a little bit about the epsilon, the dissipation of kinetic energy. Unlike the current version of Puma, this model neglects dissipative heating as a local heating term. However, it doesn't want to violate conservation of energy, so the energy that's lost by the fact that energy has been turned into kinetic energy and then it's dissipated and forgotten about, it finds out how much energy that was by doing a global energy sum, which is called the energy correction, and then reinserting a heating rate to balance that loss of energy uniformly within the whole atmosphere. And it does that interactively, time step by time step, so the model is always in energetic balance. So this is what we actually are diagnosed as the energy correction, and it turns out, as it should be, that the energy correction term, which is about 3.5 watts per square meter averaged over the world, is very similar indeed to the conversion rate between available potential energy and kinetic energy, also diagnosed from the model. So it is therefore very likely that this is really what it's mopping up. It is mopping up the fact that kinetic energy is being created and then dissipated. And that's true in famous and AOGCM3, although they don't have exactly the same numbers. And there is a small difference between these terms, which is due to some error that we haven't managed to find in the model formulation, but it is fractionally is quite a small term. But to gain additional confidence that we know what is causing what's responsible for the epsilon, Salvatore did also look into the individual terms that should be responsible in the model for dissipating kinetic energy. And the sum of these various terms does more or less equal the energy correction, so we can have a reasonable confidence that we can understand it. So about half of it comes from friction in the boundary layer. Then there's the effect of the diffusion of momentum in the atmosphere, which is actually formulated as a del squared or del to the fourth term. There's the vertical transfer of momentum by convection, and then there's gravity wave drag. So these terms are not negligible, but relatively small compared with that one. So we understand this term relatively well. To do the entire diagnostic heat entry budget, therefore, we need a sum of these kinds of terms over all the processes K that occur in all the compartments C of the model, meaning the atmosphere, the ocean, and the surface. And so we diagnose each of these things in a 50-year integration of the model under pre-industrial CO2 concentration, what we would call a control climate. So the things for which we therefore have answers are the radiation terms, which are not including in the material entropy production, the dissipation, which I've just been talking about, and then a term that is the sum of sensible and latent heating. I already explained that we have to lump, in the end, we have to lump all the latent heat terms together. But in fact, we also can't separate out the sensible heating because in parts of the model, the prognostic variables that it's actually transporting aren't humidity and temperature separately, but linear combinations of them. And this is so that it doesn't have to worry about changes of phase during some processes. But that means it's essentially agnostic in some cases about whether heating is occurring because of condensation or because of sensible heat convergence. So we can't separate the two in all places. And then we have So that term there is all these: boundary layer, stratiform cloud, precipitation, and convection. Then in the ocean, we have processes that we can also diagnose. The ocean is actually a bit easier to deal with because most of its heat transport processes do have a zero global sum anyway. So they are like mixed layer mixing, which is a local process, diffusion, advection, and each of these separately can be diagnosed. And then in square brackets at the end, we've got two other things. We've got diffusion of temperature and moisture, hyperdiffusion again of temperature and moisture. And there shouldn't be an entropy contribution from the advection because the advection step is supposed to be adiabatic, but numerically there may be small inaccuracies, so that may contribute as well. Here are the maps of the vertical integrals of some of these terms. So the energy correction term, as I said, was applied as a uniform heating rate within the atmosphere, but that means it's a non-uniform power. And here it is expressed as an entropy flux, entropy production term. So it's larger where the temperature is colder, because the temperature appears in the denominator. So it's bigger towards the poles, and it's smaller where topography is higher because there's less mass of atmosphere, and because it's a heating term in kelvins per second, that affects the size of this. So clearly this distribution doesn't really have any physical meaning. It would be better, of course, to put the frictional heating into the model at the place where it actually occurs, which is not entirely possible. In the case of the hyperdiffusion term, for instance, there isn't an equivalent formulation that would tell you where the dissipation had happened because there isn't really a stress involved. But with some terms it can be done, and in fact Salvatore did do this, and it makes very little difference to the climate or to the other diagnostics, so we don't think this is an important issue in the case of this model. Then here we have three terms which in the end have to be added up because they separately don't have a zero energy sum, but they show essentially the structure of diabatic heating in the boundary layer by the large scale precipitation scheme and by the convection scheme. Of course, this mostly happens in mid latitudes and this mostly happens at low latitudes. So these are almost the same thing as heating rates, but they've got the temperature in the denominator. Yeah.
While you're on that, are you talking about where it's coldest, but in the Antarctic that's not quite true.
But it's high there. It's high there.
Oh, okay.
Yeah. Okay. That's the reason there. This allows us then to produce results for the global entropy production by these various material terms and compare it with the other diagnoses. But in fact, there are really only two other diagnoses with sort of comparable models. There's the one that Klaus did with Klausim, and there's another one that Goody did earlier, not really with special diagnostics, but by making estimates from the GIST GCM. And you see that HADCM3 and FAMOUS get rather similar numbers for material entropy reduction, 50 milliwatts per square meter per Kelvin, lying between these other ones. And it is rather interesting that these numbers are so similar, and it shows that resolution is not the dominant term, at any rate, in the production of entropy, as far as models are concerned. And lying between these two, but we can't really say with only a sample of 4, two of which are very similar, how the spread of GCMs generally would be, and it would be interesting to know more. It could be an interesting diagnostic of GCMs. The kinetic energy dissipation is a significant part of it, a quarter of it or so in our models. And again, you see a spread amongst models in this term. I said that we couldn't tell for sure what the sensible heating is, but it's possible to make a rough estimate of how much it is, and you see that it's not very much of the material and entropy production. Much more is due to the hydrological cycle. So the hydrological cycle is the dominant term in entropy production in this model and indeed in the other models. The planetary entropy production, which involves the irreversible radiation term, is enormous by comparison. And we've decided at the outset that we're not going to take any notice of most of this. And then the bottom line is the sum of these terms, and you can see that we've actually closed the budget quite accurately. So the remaining residual is comparable with interannual variability, so you could just regard that as being in the noise. But it was quite hard to do this. It required a lot of detailed diagnostics, so it's not surprising perhaps that maybe it's not closed in these cases just because there are a few things that haven't been included, but Klaus perhaps could comment more on that. But in the end, the fact that we do close the budget, I think, gives us some confidence that we haven't forgotten something at any rate. Then the other terms I mentioned, hyperdiffusion in the atmosphere and mixing in the ocean, are both very small by comparison. And it is interesting that the ocean contributes very little indeed to the climate entropy production.
Yeah, sorry to interrupt you. I missed something obvious, and maybe others have missed that as well. How you get to 0 while all the terms above are positive?
Oh, well, because the radiation, which is included too. Yeah. Sorry, yeah. Thanks for pointing that out. Okay, so, well, what are we going to do with this next? So the main idea, as I said at the beginning, is that if MEP holds, it could be a useful integral principle which we could apply to GCMs. Now, there's a possible corollary, which seems rather doubtful, that the model with the largest entropy production would be the most realistic. But that's kind of an idea that the principle might suggest to you. If the real system is producing entropy at the maximum rate, then maybe you can improve. If you were improving a model, you get more entropy production. But it's clear that that's not really going to work, because obviously you can imagine inventing a completely ridiculous model simply to produce lots of entropy. So that is a very doubtful corollary indeed. Nonetheless, this idea has kind of been employed. This is the kind of idea of tuning that to some extent, and I'll come to this. I'll show you. Well, let me show you now. This is kind of the idea that was done in this paper, that taking a particular GCM, you vary some parameters and look to see how the entropy production or the kinetic energy dissipation varies as a function of these parameters. And it turns out that for these 4 parameters, variations in this model, you do get a peak in both of those quantities at values which are quite near to the standard values they'd chosen anyway, which are the ones that give the most realistic climate in that model. So that's the kind of idea which suggests that maybe you could use it as a tuning, this sort of principle. And Paltridge appears to have had that sort of idea too, that the realistic solution, this is talking about the real world, but would involve the preferential selection of one of the possible formats that the system itself could assume, assuming that there are sufficient degrees of freedom for it actually to try out any possible format. So it raises the question about how one could test MEP in a GCM. What does it mean to consider the different states that GCM could realize and to evaluate their entropies and see which one is biggest? Because the problem is that any GCM in general will give only one climate state. That's its solution. It's possible that there might be discontinuous climates, that maybe with the same boundary conditions you could get, say, a snowball Earth or a state with a collapsed meridional overturning circulation in the ocean. So those would be different states, but really that's not the kind of spread of states we're thinking about. We're thinking about states that are relatively near to the tunings we've already used, for example, and we want to know which one was the best tuning. And the only way that appears tractable was the one I just showed, that we would examine the material entropy production as a function of some free internal parameters in the model which represent physics we're not explicitly resolving. And of course, if this did turn out to be useful, it would be valuable because parameter choices are a large source of systematic uncertainty in GCM modeling and in prediction of climate change, therefore. Now, the previous work that's been done on this kind of thing involves GCMs, as I've already said, which are dry, or I haven't said that, but otherwise simplified. And a common simplification is that it's a dry GCM. And as we've seen, latent heat is the most important part of the climate entropy production. So that is quite a severe limitation. And it's not one that applies to famous. And we wanted to choose which parameters we were going to vary, and we decided that we would choose parameters that were already shown by this study, quantifying uncertainty in model predictions, to be very influential on climate change, in fact. They're important in the uncertainty of climate sensitivity. That's not the same thing as saying they're very influential on climate, but in fact that is closely related, especially as the most influential ones are the ones that influence clouds. And so they do influence the climate as well as the climate change. And the ones we chose to examine are the convective entrainment rate, which determines how rapidly environmental air is mixed into an ascending convective plume. So I've called this nu, but on some slides it's called E or epsilon, but epsilon's confusing because we use that for dissipation rate. So I tried to change the notation, and the cloud dropped it to rain conversion rate, which, well, it's sort of obvious. It determines how quickly the rain falls out of the clouds, so how you're removing moisture. Both these quantities are very uncertain, and they are linked to turbulent processes which are not resolved in the model, and to cloud feedbacks. So we can examine our global integral quantities, the material entropy production, planetary entropy production, generation and dissipation of kinetic energy, as functions of these parameters. And we do that by running famous for 100 years with each parameter set. It has to spin up for a while, so then we evaluate the climate from the last 50 years. And it's because we have to do a lot of runs with different parameters that it is valuable to have a fast model. That's why famous was chosen. Salvatore looked at a few other parameters as well, and they don't, some parameters don't really show a particularly systematic behavior at all, but there's a big variability. Others show qualitatively similar behavior to the ones illustrated here, so it wouldn't add more to illustrate other parameters. If we reduce the convective entrainment rate from its standard value of 3 to 0.1, the result is there's less entrainment, so that means that convective plumes penetrate higher, and we get more diabatic heating high in the atmosphere at low latitudes in particular. The Hadley circulation gets stronger, and there's also less descent, therefore, surrounding it. If we do the reverse, the diabatic heating becomes more restricted to lower parts of the atmosphere. And corresponding to this, reducing nu means that we get lots of warming aloft where latent heat is being released. This is an anomaly compared with the standard climate. And we get, when we increase nu, we get anomalous cooling here, where there's less latent heat release going on high up in the atmosphere. And those are the sort of principal things one would expect to see. And there are other features here for which we haven't got a proper explanation. I don't really know what's going on at high latitudes here. This warming might be a response to the fact there's perhaps less cloud in these regions. But so this is to show that the climate is certainly responding to these parameters. Choosing a range of different values for nu, in fact the planetary entropy production correspondingly and the material entropy production do vary with nu. But as you see, the variation with nu is monotonic. As we increase the entrainment rate, the entropy production monotonically declines, both the material and the planetary entropy production. So the fact that we've decided to concentrate on the material entropy production is not going to affect the conclusion. On the other hand, the contribution that comes from KE dissipation specifically does have a maximum as we vary nu, and this maximum is not at the standard value of 3, but it's at 1.5, so it's some way away, but not totally different. So that is intriguing. Now if we look at the other one, CT, so this is the cloud lifetime effect. When we increase this parameter, when we reduce this parameter, that means we are reducing the efficiency of conversion of cloud moisture to rain, and this has the effect of increasing the cloudiness. So that is like let me get this the right way around. So the entrainment tends to reduce the cloudiness. I'll come to the cloudiness in a moment. All right, no, let me describe this first. The point is that the cloudiness is the explanation. The increasing the entrainment rate has the opposite effect to increasing the efficiency of conversion of cloud water into rain. And reducing the entrainment rate, likewise, because this pattern looks like this one, and this pattern looks like this one. And this is because they're doing opposite things to the clouds. Oops. Sorry. I'll get there in a moment. Push the wrong button. It's because they're doing opposite things to the cloud. So when we reduce the entrainment rate, we reduce the cloudiness. We increase the cloudiness because we're sort of encouraging the convection. And when we increase the entrainment rate, we reduce the cloudiness. And when we vary the parameter that involves how quickly we're getting rid of clouds, so we make clouds disappear more quickly, we reduce the cloudiness. If they disappear less quickly, we increase the cloudiness. And you see these fields have very similar forms, and that is why they're having opposite effects on the temperature structure of the atmosphere. And I think therefore that the fact that they're having similar opposite effects on diabatic heating is because the cloudiness itself is driving the convection from the surface in the case where we're varying CT. But the details of this are not really germane to the argument. The point is that CT is also having a large effect on the climate, but it turns out to be qualitatively a similar sort of effect, but with the opposite sign of variation of parameter. And so it's therefore not surprising that the material entropy production also depends monotonically on this parameter, but in the opposite way. So if we increase the parameter, we increase the entropy production rate. And as we found with the entrainment rate parameter, we have a maximum kinetic energy dissipation as well at an intermediate value, which again is not the standard value, but not so far away from it. That's the red line is a standard value. So what if we vary both of these things together? And so that's what's done here. So this is the entrainment rate on the x-axis, this is CT. So we're just varying, you don't have to worry so much about what the parameters are. We're varying two parameters together. Now we found before that increasing the entrainment rate, we find that increasing the entrainment rate generally has the effect of cooling down the global average temperature. And that's because, on average, it's increasing the cloudiness. Whereas if we reduce the CT, we cool down the global average temperature. And similarly, that's because it's having an effect on the cloudiness. So both of these parameters are affecting the cloudiness and therefore the radiation budget of the Earth and therefore the global average surface temperature. And they're sort of compensating. So while there isn't a diagonal line which is constant, you can see they're having opposite effects on the temperature. Now when you increase the radiation available, and that's raised the temperature, you're also going to increase the precipitation. So this is, in a way, like an experiment where you've increased the irradiance of the sun. You get the same thing. You warm up the climate, you get more precipitation. In a warmer climate, the hydrological cycle is more active. There's more precipitation, and so since the hydrological cycle dominates material entropy production, therefore the material entropy production has a similar sort of form to this. And it turns out that variation in material entropy production is dominating variation in planetary entropy production, so that also has a similar form. So all the things are varying monotonically together because the variation of the parameters fundamentally is changing the Earth's radiation budget. Okay, so that's not really the effect we were looking for when we started out. And I'll come back to that in a moment. Just after we looked at this, so this is the kinetic energy dissipation entropy production term. That is the entropy production, this is the dissipation itself, plotted on the same axes, and you can see it here, because there was a maximum on both the individual axes, there is also a maximum here in this term. which is quite close to the standard value. The crosses indicate the parameter combinations which will actually run, and there are most of them down here. There are relatively few over here and over here, because these climates are far from the standard climate of the model. They're much less realistic, and in fact it was quite difficult to persuade the model to run with those parameter combinations, because it's just an unfeasible climate and other schemes cause problems and the model crashes eventually. And most of the kinetic energy dissipation, as I said before, is in the boundary layer, so this term is similar to this one. So to summarize, we've got monotonic behavior, which is related to the overall energy budget in the material entropy production, but the part that comes from the dissipation alone has a maximum at certain parameter combinations. So because the material entropy reduction is increasing monotonically with global average temperature, because the surface absorbed shortwave radiation is doing that, because of the effect on cloudiness. And that means that the trade-off mechanism that I described at the beginning can't operate, because the idea then was you've got fixed absorption in the tropical box and the polar box, and you're going to have some kind of trade-off between how much of that you transport meridionally compared with how much is re-radiated locally. But if you are not fixing the insulation, of course this is not going to work, because what is actually dominating is the total throughput of energy through the system. So in order to test MEP, which is in a way which is comparable to the two-box model, we have to fix the absorbed shortwave radiation. So we do that by making the clouds transparent and fixing the surface albedo, a snow and ice-free value. Consequently, because the albedo of the Earth has been lowered a lot, of course we tend to get a much warmer climate, and because we're interested in something that's like a realistic climate, we also reduce the solar irradiance. So we get more or less the same global average temperature as before. Now, parameter CT, which directly affects the clouds, has no influence, because we don't really care about the clouds. But it turns out the entrainment rate still does have an effect, because it is directly influencing the transfer of latent heat from the surface into the atmosphere. So we just look at the invariation with nu, and it turns out that now we do get a maximum in the dissipation and in the material entropy production, and they're not exactly the same place, but they're in a similar sort of place, not where they were before, which was down here, but up here. But the maximum is quite shallow, but it is a maximum. However, it's still not due to the trade-off mechanism. So there are a number of quantities plotted here. The brightness temperature of the Earth is basically the measure of the OLR, and because we've now fixed the absorbed shortwave radiation, the OLR is constant. So the brightness temperature is not a function of the entrainment rate parameter. The equator to pole gradient in temperature has a minimum at the point where we have the maximum entropy production. And that's not what we expect in the trade-off mechanism, where we expect, as we vary the parameter between one extreme and the other, the equator to pole temperature contrast goes from its maximum radiative value to 0. Whereas what's happening here is it starts to go down and then it goes up again. Okay, and this is it here. It comes down. Now it's plotted here against poleward heat flux. So as the equator to pole temperature contrast goes down, the poleward heat flux goes up, which is what we expect in the trade-off mechanism. But again, this doesn't continue like this and like this, so that their product would be an extremum. Instead, this turns around and comes back again as well after a while. So this maximum is not coming about because of the trade-off. It's coming about in the same way that Axel suggested, in fact, in his paper where he varied the von Karman constant, that the maximum entropy production is coming about at the point where the maximum heat transport is occurring. And as we vary this parameter, it doesn't have a monotonic effect on the meridional heat transport, because it's not having a monotonic effect in some sense on the dynamics of the atmosphere. At one level, perhaps we don't have any barochronicity. At the other end, we have not enough because it becomes barotropic or something like that. We haven't looked in detail, but because the dominant thing is the meridional heat transport due to barochronicity, this parameter is not able to vary the climate system over a range that encompasses all possible efficiencies of meridional heat transport. So we don't get the trade-off of the box model. All right, so we haven't managed to demonstrate the same thing that happens in the box model. Box models with no explicit or dynamic physics or dynamics give MEP by this trade-off. That didn't work in famous with unconstrained absorbed shortwave, because instead the overall absorption of shortwave dominated as the parameters are varied. When we fix the absorbed shortwave, we do get an MEP maximum, but again, it's not by the trade-off mechanism. So we're going to construct, finally, an intermediate model, a zonal mean model, with half the latitudinal resolution of famous and the vertical resolution that famous has got. And so this model was completely unconstrained. This model was apparently too constrained by physics. And in this model we got rid of some physics, but we still don't get the trade-off mechanism. So now we're going to get rid of all the physics again. We'll just have more boxes than two. So we go back to a model now where all we are going to require is a local energy balance. That's not right. Oh yeah, of course, the global integral of radiation has got to be 0. Locally it's not 0. What happens locally is, by Michel's question, is the material heat divergence exactly balances the radiative heat convergence. So we're not actually going to diagnose anymore the processes that are moving the heat around materially. We just assume that locally material heat convergence is balanced by radiation. And so the material heat convergence is just the residual. So in this model, we prescribe the shortwave heating rates from famous. So they're sort of realistic, and they look like this, and this is determined by where clouds and water vapor are in the atmosphere. We can't prescribe the long wave as well, because we want the models to determine the temperature. That's the aim of this model, like with the two-box model. So instead what we prescribe is long wave transmissivity, or emissivity, which we assume to be 1 minus transmissivity, which we diagnose from famous. So we prescribe that. So what we do is vary the temperature field in order to get a solution. And then we see what the material entropy production is as a result. Now first of all, before doing that for MEP, we can consider a number of cases that were constructed by Salvatore by hand to illustrate particular things that might happen. And firstly, we have the extreme cases of 0 entropy production. So this is like the limits of the box model, and 0 entropy production can come about by two means, and the real solution we expect to lie between them. So one of the ways we can get 0 entropy production is by having no temperature contrast. So we have the same temperature everywhere, okay? And that's the green line here. So the model's climate looks like this, as a function of surface temperature as a function of latitude, and of course it's warmer in the tropics. And then the green line has no temperature contrast. So consequently, the poles are warmer than they should be, and we have to have more meridional heat flux than the standard model does. So this is the northward meridional heat flux. So you see it's a maximum in mid-latitudes, a maximum northward in northern mid-latitudes, a maximum southward in southern mid-latitudes. And we need more of it if we make the temperatures uniform. And we've made the temperatures uniform in the vertical as well. And so that means the upper atmosphere is much warmer than it is in the real climate, so we have to have much more upward vertical heat flux to accomplish that, compared with the standard solution, which is this one, showing upward heat flux as a function of height. Then the other extreme is the red dotted line, which is no heat fluxes. That's another way of achieving no entropy production, of course. And so in the case of no heat fluxes, we have, therefore, tropics which are much warmer than they are in the real climate, and poles which are much colder. So we have a much stronger temperature contrast, but we have no horizontal heat flux. And in the vertical, we have no vertical heat transport, and that means instead we have a much stronger vertical temperature gradient. Basically, because we're not allowing any material heat flux, that means that the surface has got to radiate to space, because the only way it can lose heat is by long wave radiation. And because the atmosphere is rather opaque, that means the surface has got to get extremely warm. And indeed, the lapse rate is rather strong in the atmosphere. So that's not a realistic solution, of course, but that's the other end member. Now, a good thing about the box model is we can look at horizontal and vertical separately, which is impossible to do in the GCM, of course, but that's a 3D model. So we can also consider extreme cases with vertical entropy production only, so no horizontal entropy production, but we're going to allow vertical entropy production. So no horizontal entropy production can again be accomplished by having no horizontal temperature contrast, which is in green again, okay? So we have no horizontal temperature contrast, but we do have a vertical temperature contrast, but no horizontal temperature contrast means, again, we have to heat up the poles, so we have lots of meridional heat flux. But because now we're not affecting the vertical, this solution exactly coincides with the model's own solution. Okay, so the blue line and the green line are coincident. And then again, we have the other extreme of no horizontal heat transport. So that one is flat, The red line here coincides with the blue line. It doesn't affect the vertical as far as climatology is concerned. But we have a stronger equator to pole temperature contrast than in the red case than the standard blue case. So again, that's sort of what we expect, and that's like the trade-off you would get in the two-box model horizontally. And one other case to consider, one of no vertical temperature contrast, which means we only have horizontal entropy production. In that case, that's like, yeah, okay. Well, the effect of that is to make, because we have no vertical temperature contrast, that's like having an average temperature at every place. So the surface temperature becomes rather colder, but we've still got a surface equator to pole temperature contrast. And we've still got a poleward heat flux, but we haven't got any vertical temperature contrast, so we won't have any vertical entropy production. So these cases are just kind of like taking realism in one dimension, but suppressing it in the other in different ways in order to get rid of separately the horizontal and vertical entropy production. So now finally, we look at the MEP solution, which is where we allow the temperatures to be varied, and this is done with an iterative variational procedure to find the temperatures that will satisfy the heat balance, and also at the same time, so that set of temperatures that satisfy the heat balance but maximize the entropy production with the prescribed shortwave and the prescribed longwave emissivity. And so the MEP solution is shown in purple here. And so the interesting thing is that in terms of its surface temperature as a function of latitude and its meridional heat flux, it looks very much like the model's own climate in blue. But in terms of its vertical structure, it looks quite a lot different. So the MEP solution would like it to be rather cold near the surface and rather warm in the upper atmosphere, and also have a big contrast between the surface and the lowest parts of the atmosphere, because by having a big contrast there, it can generate a lot of entropy because it's putting a big heat flux through a large temperature difference. And so here is the heat flux, okay? And the heat flux, because it's coming to heat up this part of the atmosphere, is large. Not as large as it was in these cases where we completely abolished vertical temperature variation, but larger than the standard blue case. So when you ask the model to choose the temperatures that will maximize the entropy production, what it chooses to do is to make the surface as warm as possible and the upper atmosphere as cold as possible, so that it can lose heat to space from a low temperature. And that means that overall it will generate the largest amount of material entropy. But unfortunately, it's not a very realistic solution. That's the trouble. So we got rid of all the physics and found a solution, but it's not very realistic. Okay, so just to put that in numbers. So this is the standard case, the model's own simulated climate. So the total material entropy reduction is 47. That's a bit less than I showed before, which was 52 or 53, diagnosed directly from the model. And the reason for that is that when it's done offline, we're using time means of the quantities, and it turns out that the internal variability of the climate actually increases the entropy production slightly. And when we suppress horizontal and vertical entropy contrasts separately, we see that the total that we get is, we can decompose the total entropy reduction quite neatly into a vertical bit and a horizontal bit. And we get this vertical bit only in the cases where we suppressed a horizontal entropy reduction, and we get the horizontal bit only in the case where we suppressed vertical entropy reduction, and they add up to give the same total, more or less, as the model's own solution, suggesting that vertical and horizontal entropy reduction are sort of orthogonal, they're kind of independent, you can also get reasonable results for that with a box model, by coupling a horizontal two-box model to a vertical two-box model. And the entropy production is dominated by the vertical heat transport, not the horizontal heat transport. The maximum entropy production solution, therefore, in the GCM, well, it's not in the GCM, this analog of the GCM is reached by increasing the vertical entropy production. In fact, the horizontal entropy production stays roughly as it was before. But the solution that's achieved is unphysical, because this box model is not having to respect constraints that the GCM has got that determine what the realistic lapse rate is, for example. So finally, to summarize, entropy production and its components in terms of the processes that are going on in the GCM have been diagnosed in FAMOUS and in HADCM3. And the climate material entropy reduction is about 50 milliwatts per square metre per Kelvin in both of them, which lies between the two previous estimates with models of similar sort of complexity. Most of this is due to sensible and latent heat transport, mostly, in fact, latent heat transport, and the majority of the rest is due to dissipation of Ke. To test the conjecture, we varied uncertain model parameters. That's the only way we could think of doing it, to test the idea that MEP would somehow select the most realistic climate. No maximum, however, is found in the material entropy production because that's dominated by latent heat release and it correlates with global average temperature and varies with the planetary albedo, and this all has to do with the effect of the planetary albedo on the energy balance of the system. But there is a maximum in Ke dissipation, which is therefore consistent with the idea of the conjecture of Lorentz. If we fix the albedo, we do get a maximum in material entropy reduction, but not by the mechanism that we get in the box model, by something else that has to do with the behavior of dynamics as we vary other parameters in the model. The entropy production by vertical material heat transport turns out in our multi-box model to be much larger than that by the horizontal heat transport. And if we fix it, if we fix parameters and allow the temperature to be varied regardless of any other physics, we can maximize the entropy, and that comes about by maximizing vertical entropy production, but it achieves an unrealistic solution. So it seems like these experiments, this is a provocative way of putting it, but kind of suggests this solution that in some sense the GCM is at one end of the scale. The GCM is trying to solve the problem with many constraints. Many constraints, that is the physics, as far as we know, to the system is built into the model, and it will only give us one answer, right? But if we know the constraints and we know them accurately, we already know the answer. We just have to run the model to find out what it is. So in that case, MEP doesn't really help us to find the solution. If we've got the model, we can just ask the model what the solution is. On the other hand, if we relax the constraints, which is done to the extreme extent in a box model, by not having any physical constraints, so not having any reason why the surface shouldn't be far warmer than it is now, and an enormous lapse rate. If we get rid of the physics that determines those things, we get MEP, but we get a wrong answer, a clearly wrong answer. So in that case, MEP isn't really helping us either because it's not telling us the right solution. So this seems to be a bit of a sort of discouraging way of looking at MEP. It is, however, quite possible, as was argued recently, I think in papers of Roderick's and Axel's, that we perhaps should interpret this not necessarily as a physical principle, which is an alternative to running the model, but as a quicker way of getting the right answer if we had formulated the problem correctly. And that's not inconsistent with this statement. But there does seem to be some hope for the part that comes from kinetic energy dissipation, which is sort of consistent with where Axel was leading. So in experiments with dry models, such as have been done before, of course, there isn't the dominant term that comes from the hydrological cycle. The only entropy production is due to dissipation of kinetic energy. So therefore, by construction, kinetic energy maximization of dissipation and maximization of entropy reduction have got to be the same thing, essentially, apart from the T in the denominator, which is relatively constant. But in the realistic situation, that's not the case. However, it might be the case that the maximum dissipation does apply and does tell us something about the horizontal heat transport, maybe. The GCM suggests that that could be the case, and again, that's sort of consistent with Axel's earlier work with Puma. So that's it.
Time for questions? Tim?
Yeah, I was sort of intrigued by this maximum in Ke dissipation that you found. And you made the comment, that its maximum doesn't correspond exactly to what is traditionally thought to be the correct parameters.
Yeah.
And it kind of got me on a slightly, I have to say, philosophical train of thought about sort of something we discussed earlier in the week, which is what is the nature of uncertainty in model parameters. And it seems to me, if we say the uncertainty is kind of epistemic, in the sense that there is a well-defined best value, and we just don't know it because we don't have enough observations, then this would perhaps be a rather powerful sort of way to determine those parameters. But on the other hand, if the uncertainty of the model parameters really is because the the parametrization is not properly representing what's actually going on in the real system. So although you talk about entrainment, I mean that applies to obviously a single convective cloud, but whether it's a relevant parameter for a grid box, 100 kilometers is another matter. And if that's the case, then I would think it's a rather dangerous thing to do to use these maxima in K dissipation fixed parameters, because the model is not therefore the same equations as the real world, and you could be driven up a wrong path entirely.
Well, I tend to agree with your latter point of view. That it's another sort of trade-off. In fact, in tuning models, a trade-off of wrongness. Although we don't have infinite observations, we do have enough observations to be sure that any tuning of a model like this is certainly wrong. And so it's a question of where we would like the errors to be mostly, rather than finding a single right answer, because there isn't any fully right answer. And therefore there is indeed a balance of what's going wrong in the dynamics against what's wrong with the physical parameterizations, as I expect we would normally suspect that there is.
I had another question, but just as to reply to that. Well, when you put a parameterization in a model, it's because you believe that it's informative about the physical constraints. So to some extent, even if it is an approximation or, a model, for example, for boundary layer turbulence, if you put it in it, you think that, it's the structure of that equation is constraining. So if MEP applies given that constraint, there is nothing wrong in trying to find a parameter that will maximize production of entropy with that constraint.
Yes. Well, there's nothing wrong with it, but there's no guarantee it will deliver a realistic model, I suppose. Of course
it's a test of your constraint.
I mean,
maybe you put the wrong constraint, so the parameterization is wrong.
That's right.
In that case, it's informative as well.
Well, that's my real question, my original question. It's a technical point. I'm slightly uncomfortable with your kinetic energy, dissipation correction. I can see that the dissipation of kinetic energy is not explicitly taken into account, so you have re-injected. That's all right. But what happens with the heat that's being transformed into kinetic energy? I realize that in a climate model, you first have sensible heat transformed into potential energy and then transformed into kinetic energy. Is this cycle right as well?
Well, it's energetically closed in the global sum by the energy correction, but it's not locally correct because the heat's not going in the right place. So effectively that cycle, I suppose, takes heat from one place to another place, the place where it's converted into potential energy in some sense, the place where the kinetic energy is dissipated. And the model's not doing that properly. But it doesn't seem to be, in our experiments, a very important climate effect. Does that make sense?
I guess I missed a point, but we definitely have to talk about
it.
Okay.
So I have two questions, one of which is a very kind of naive question, and I'm just wondering, with the result of the vertical transport being so important, Ed Lorenz, who had thought of many things very deeply, whilst he was doing available potential energy, and also come up with the concept of gross static stability, and in effect an unavailable potential energy in the vertical. And is that constraint being obeyed by the MEP formalism at this point?
Well, I'm sure it isn't being. If it was, it would just be chance. I mean, because no constraint is built into that way of doing it. Of course, if you build in another constraint, you will get a more realistic solution. But you're also constraining the sort of space in which MEP has to operate.
The reason I brought up that, which is my naive question, is because when you started with Paltridge's result, which was APE loss being equivalent to kinetic energy dissipation. And you have the greatest success in describing kinetic energy dissipation with MEP, and less with the vertical transport. And yet that's the one that happens very quickly and ought to be more standard. My second question is a philosophical question, so I'm going to just throw this out. Is it indeed correct to ask for conservation of all these global quantities within the context of a finite resolution model? The system is really an open system from the perspective of wave number space. You're going from a closed system of wave numbers to the rest of the system. And is it true that all the energy is trapped within the context of a coarse resolution
I never thought about that.
representation?
Of course, people are just, in a way, they just take it as axiomatic that we must conserve energy. So I don't know if that's an interesting question to talk about, isn't it? I don't know the answer to that.
to get a stable control plan without it.
You could introduce non-conservations in parameterization effectively to work. I mean, for example,
You're taking away the only constraints I had.
the heat convergence does that. Heat convergence does that in a slab model. It mops up non-conservation. That's not why it's there, but you know.
Isn't it what you are doing? I mean,
Yeah.
so the high wave numbers get converted into heat.
Yeah.
Right.
But should they be
Is
converted
that-
into heat on the scale of the coarse resolution model?
Right. Yeah. Do you have a point, Axel?
I remember part of it. So the parameters that we picked,
Yeah.
can you think of similar trade-offs that would let you to speculate that there should be a maximum with respect to this? When you didn't, I think you didn't talk much about it when you said we varied.
I suppose that we haven't found the parameter that gives a sufficiently wide range of climates actually realised to produce the ordinary trade-off as you've described it.
Yeah, because I mean the thing is, I mean,
Yeah.
just to sort of sketch out sort of perhaps the most unrealistic parameter that you could vary is you say, oh well, I vary planetary albedo
Yeah.
and see what state of MEP I can get.
Yeah.
And of course, they get the greatest entropy reduction
Yeah.
when you have a black planet,
Yeah.
right? And that's unreasonable.
Well, that's right.
And I think it
Yeah.
comes back to the question, and I mean, we can probably pick this up in the discussion later, is that I think it's always a problem, which entropy production should we?
Yeah, it is. I think that's right. I would say, as a result of this, that vertical entropy reduction should not be maximised if we're going to use MEP, because that clearly doesn't work. Horizontal, it might be the maximisation of horizontal entropy reduction is actually coming about because of the maximisation of horizontal energy.
Or the dissipation of kinetic energy.
Okay. Oh, yeah. I mean, these things are related. That's right. That's right. But you're right. I mean, of course, there are ways of getting higher entropy reduction than this. If we allowed to do what it wanted to do with long wave and short wave emissivity, I think it would make the surface black. The atmosphere completely transparent to short wave, and the atmosphere completely opaque to long wave.
Okay, any other points? Thank you very much for that. We've got coffee break now, but afterwards we're going to have a discussion session like the one that John T ran a few days back. I think Roddy's going to do sharing of that. We're going to try and run it like John T did, because that seemed to work quite well, which is to give people the opportunity to write questions up on the board that we then discuss. But I want to first of all check we can rub this out. But we'll be back at 3:30. If people want to write up questions in the meantime, once we've rubbed things out, then by all means do.